Hello, and welcome to the OpenBrIM platform. In this video, we will demonstrate how an AI-powered assistant is integrated with parametric bridge modeling. Two applications are shown on the screen. On the left is an AI assistant that processes natural language commands. On the right is OpenBrIM, the cloud-based parametric bridge engineering platform. In a traditional workflow, creating a bridge model required defining geometric parameters one by one, entering section and material properties manually, and applying each revision individually. In this workflow, however, it is sufficient to express the design input in natural language. The commands given to the assistant are automatically translated into a model within the OpenBrIM platform. The geometry, parameters, and components are generated dynamically in accordance with the command. In this way, the definition process and the modeling process are merged into a single step. Let us now examine this integration in practice. Into what structural outputs do natural language commands translate within OpenBrIM? With a single command, we ask the assistant to create three separate projects consisting of different bridge types, referencing the alignment in the folder, along with a federated 3D model that unites them. In the command, we divide the alignment into three sections according to station values. The first section is defined as a Precast I-girder bridge, the middle section as a steel I-girder bridge, and the final section, again, as a Precast I-girder bridge. We also specify the structural configuration clearly. The bridge will have 4 lanes, Hammerhead substructures will be used at all intermediate piers, and end bents at the beginning and end. We particularly emphasize that footings and piles must be included in the model. In addition, we ask that the span arrangement, plate girder dimensions, precast girder sections, and pier cap and column dimensions be optimized according to general engineering rules. No analysis or design is run at this stage. Our objective is solely to build the model. As a result, we expect 3 separate projects and a single federated model containing only the 3D model. The assistant divides the bridge into 3 parts according to the station values: precast at 625 feet, steel at 751.5 feet, and precast again at 384.9 feet. It verifies on its own that the total length corresponds exactly to the 1,761 feet alignment. The first important point we wish to highlight here is the manner in which the span arrangement is determined. The assistant optimizes the spans based on standard span-to-depth ratios and economy rules. In the precast bridges, the spans are arranged equally, 5 equal spans of 125 feet each for Bridge 1, and 3 equal spans of 128.3 feet each for Bridge 3. By contrast, in the steel bridge, Bridge 2, a 4-span continuous arrangement of 167, 209, 209, 167 feet is selected, with the ratio of end to interior spans balanced in accordance with continuous plate girder behavior. In other words, the assistant does not apply the same logic to every bridge type. In simply supported precast bridges, the equal spans are kept within an economical range, whereas in the continuous steel bridge, the span ratios are adjusted according to structural behavior. The assistant then begins creating Bridge 1 using the precast workflow. It opens the project, imports the alignment, and checks the units. It generates the superstructure, 5 spans and 7 girders for the 4-lane deck, with an ASHTO Type 6 section appropriate for the 125 feet spans. It places the support lines at the exact station values. Since the 5 equal spans land precisely on the target stations, no adjustment is required. 4 intermediate hammerhead piers and 2 end bents are then created. Here we arrive at the second important point. To run the pile cap generator, the project must be in an uncompiled state. However, when the assistant checks the model state, it detects 6 validation issues. At the end bent caps, the caps contain an unset rigid section reference, and the project is stuck in a compiled state. What is notable is that the assistant does not stop at this point or wait for user intervention. It diagnoses the root cause itself. By inspecting the bent cap, it identifies the missing reference and assigns the rigid section already present in the hammerhead piers to both end bent caps. After the correction, validation is run again, and the result is clean, zero issues. The pile cap generator is run once more. Bridge 1 is thus completed. The superstructure, 4 hammerhead piers, 2 end bents, 12 footings, and 108 piles are placed in full. This demonstrates that the system does not merely execute commands, it can diagnose and resolve technical issues that arise during the process on its own. With the same approach, the assistant creates Bridge 2 using the steel workflow. After building the superstructure, it applies the balanced continuous span arrangement it had planned at the outset and optimizes the plate girder sections according to the longest span. It increases the web depth and flange dimensions as required by the 209 feet spans. Here, too, it queries the current state of the model before changing the section, then applies the change consistently across all girders. With the addition of hammerhead piers, end bents, footings, and piles, Bridge 2 is completed. Bridge 3 is created similarly using the precast workflow, preserving the equal span logic. All 3 bridges become ready as independent projects, each with its own superstructure, substructure, and foundation system appropriate to its type. In the final stage, the assistant creates an empty project, adds only whole model 3D references for each of the 3 bridges, and synchronizes them. The bridges are united into a single federated 3D model, aligned end-to-end along the alignment curve with the correct station values. The result is exactly what we requested with a single command at the outset. The complete modeling of 3 different bridge types with their optimized spans, piers, footings, and piles, all brought together in a single federated 3D model. Moreover, throughout this process, the assistant did not merely execute commands. It made decisions according to the structural behavior of each bridge type and resolved the validation issues it encountered on its own. With that, we have seen how a single natural language command can produce 3 fully modeled bridges and a federated 3D model, demonstrating the power of combining natural language input with parametric engineering logic.